All right, good evening and welcome to our Tech Talk number 3. We're going to be presenting some really interesting information tonight. My name is Peter Tridy. I've got Gale Banks here with me. Thanks for being here tonight, Gale.
I'm loving it.
We've been talking a lot about density in the last couple of sessions, and tonight we're going to talk about some ways that we can really amp up the air density that we've been talking about. So our topic tonight is life after wide open throttle.
Exactly.
And you're going to, I'm sure, give us a little
That's
bit of
the life I've been trying to lead.
A little bit of an explanation of what you mean by that.
Yeah. First time I went to El Mirage and stood those butterflies on end in those Hillborns, and that's all there was. I went, there's got to be more than this. So I started looking into supercharging and kind of got into first supercharging. I think the first one was a nailhead Buick that I put a 671 on that went in a boat, and that would be late 50s. So in the early 60s, I started looking at turbocharging, and turbocharging was not new in the early 60s. Turbocharging had been around since about 1905 or so. A guy named Alfred Bucke invented the turbocharger to go on one of Diesel's engines that was in a locomotive that went up into the Swiss Alps. So as it got up into lower air density, power dropped off, it started smoking, and wasn't real viable. For
lower air density, that's because we're up higher in altitude.
Exactly.
So as we go up in altitude, that barometric pressure is dropping, so we have less air density available to us for the engine to breathe.
Exactly. So Bucke invented the turbocharger. Of course, we didn't have all the metallurgy we have today, and it was pretty rough. But it solved the problem, and those locomotives worked a lot better at high altitude. There was some playing around with turbocharging on World War I aircraft, and finally GE got into turbocharging, probably in the 20s, and they set the altitude record for aircraft and pushed it up like 15,000 feet higher than they'd ever gone before. They tested that engine at the top of Pikes Peak. They mounted the aircraft engine on a truck with a prop on it, drove it to 14,100 feet, top of Pikes Peak, fired it up with the turbo on it, and brought it up to full power, and pretty well developed the fuel metering and all the rest of the stuff that goes along with pushing air in an engine. So turbochargers and superchargers. I've been kind of a turbo guy, and you know, I like the turbocharging in that I can pretty well hide it within the car, and kind of inhale air off the nose of the car down there, both sides of that fascia, and just kind of push the air into the turbochargers under the hood, as opposed to the other method, which would be a supercharger. Here's an F-body with a supercharger, and right away we got an aero problem here. You know, I like to slick them up, and this is just a problem.
They just don't fit as well, do they?
No, they don't. But, you know, is that thing out in the parking lot by any chance? Did he bring it tonight? I'd love to see that thing just start up, because probably the parasitic requirement of that supercharger is more than the engine makes. So basically, we're going to talk about the density machines tonight. The density machines being turbochargers and superchargers. So what is density? Density is the mass per unit of volume. So I like to look at density when I'm starting to figure out what an engine's going to do. I start looking at density and thinking in thousands of cubic feet.
And we got into this in the last session where we talked about we're really dealing with pounds of air.
Exactly.
When we say mass, we're talking about the weight, the pounds of air that we're going to process.
Exactly. So on a standard day, The density is 76.4 pounds per 1,000 cubic feet of air.
Okay.
And if this room were down at Long Beach at sea level, that would be about what the air mass is in the room.
So this is sea level again. When we talk about standard, we're talking about a day, we're talking about numbers that are taken as a standard at a sea level atmosphere, basically.
Yeah, actually, a standard conditions is defined by the Society of Automotive Engineers. There's two different standards. This is the earlier one that all the race guys use. So a standard day is 29.9, a barometer would be 29.92 inches of mercury,
okay,
or 14.7 pounds per square inch. That's the air pressure on us right now in this room. Standard day temperature would be 60 degrees Fahrenheit, and relative humidity on a standard day, they define as zero, none.
Right. And when we looked at some of the way these numbers affect density last time, we saw that we could see pretty large swings with both the pressure and the temperature. Humidity, not so much. We saw about a 4% swing with from 0 to all the way to 100%.
Exactly. Humidity
so it
doesn't
have
move
quite as much of an
much.
impact.
Yeah.
But the other two factors have a pretty
basically, if you've got 100% humidity, it drops the density about 4.5%.
Yeah. Okay.
So it's not a big impact, but these other two are. As we talk tonight, we're going to talk in pounds. I'm not going to talk in kilograms, and I'm not going to talk in any metric units. I'm going to talk in carpenter numbers.
No euros.
Yeah, and it's okay. You know, they're easily converted into other units.
Okay, good.
So we've developed a method of reading this air density, and this is how it'll look as it comes out in production. But basically, this gauge ID is the intake density. It's a density in your intake manifold on a standard day. In other words, if your manifold is 14.7 pounds of pressure, which is ambient, your temp is 60 and your humidity is 0, you would have 76 point whatever pounds of air per 1,000 cubic feet.
Got it.
Now let's start using this for something. Let's start using it for something. If we want to make 100 horsepower, this is my rule of thumb with gasoline, we need 10 pounds of air per minute, or we need 600 pounds of air per hour.
Okay.
So that becomes the mass airflow, or MAF, requirement to make 100 horsepower.
Okay.
600 pounds per hour of air. But we got to bake the cake here. We've got other components to this, other things we add. And the other thing is fuel. So what is our fuel requirement at a 12-to-1 air-fuel ratio? And I'm using 12-to-1 because a lot of hot rods sitting out there are running 12-to-1.
That's kind of that middle of the road. If we went much richer than that, we'd probably wind up with some unburnt fuel coming through the system. If we went much leaner than that, we could probably go a little bit leaner and be a little more efficient. But if we go too far, if we go too lean, then we're going to have some issues.
Well, go too lean and you burn a piston.
Yeah.
Go too rich and it just lays down. 12-to-1, a lot of guys running blowers are running more than that just to cool it down, especially if you're running a supercharger without an intercooler. So what's my fuel requirement then? If I've got 600 pounds of air and I'm running 12-to-1, I got to divide 600 by 12 to come out with my fuel requirement at 12-to-1. Mm-hmm. And that comes out to be 50 pounds of gasoline an hour. So there's my gasoline flow. Average fuel efficiency on a hot rod engine, it takes about a half a pound of fuel to make 1 horsepower for an hour. And that's called the brake-specific fuel consumption. It's measured on an engine dynamometer normally. That's the brake part of that. Dynos are called brakes. Right. So now I've got 50 pounds an hour. It takes a half a pound per horsepower per hour. That equals 100 horsepower.
Get us that 100 horsepower.
So 10 pounds of air per minute, I just walked you all the way through air, fuel, and engine efficiency and right back to the 100 horsepower. Engines displace air. That's what they do.
Right.
They displace air. Throttles and superchargers change the air density. That's that pounds per 1,000 cubic feet. So, typical supercharger, here you see the throttle butterflies on the top. You can change the air density by opening and closing the throttle. That's what a throttle regulates. It changes the density of the air going into the engine.
Right.
Or the weight of air per cubic foot, and the engine pumps cubic feet. So air density and RPM determine power output. If you want to pump more air through the engine, you don't have a blower, you can turn the engine faster and increase the power until you float the valves. I'm building a 427 right now. And my 427, I want to run 7,000 RPM. And my valve float will probably be around 7,400. This is a street engine. At 7,000 RPM, my 427 will draw in 869 cubic feet per minute. Ambient air density, once again, is 76.4 pounds per cubic foot. We're starting with that. Mm-hmm. So, if I've got 869 CFM, and I know 1,000 CFM is 76.4, mm-hmm. Well, 869 is 87% roughly.
Yeah.
So, 0.869 times 76.4 gives us 66.4 pounds per minute.
Okay.
Or 664 horsepower.
That's using that.
Bam.
That 10 pounds.
There you are.
Gives us that
10 pounds per 100.
Yeah.
Done.
Got it.
I know what I can do at 7,000 RPM with that engine. That's at wide open throttle, WOT. But there will be losses.
Right.
So.
And we talked about some of those losses when we talked about the four-stroke process. There's always going to be some pumping losses. There's going to be some parasitic losses. There's always something that's going to take away
from the nose of the car to the intake valve.
Yeah.
There's going to be some drag. There's going to be some losses. And we talked about how to overcome those losses with ram air and other stuff last time. But there will be losses, and the losses can be pretty profound. Here we've got a big block Chevy under the hood of a pretty sweet car. You just look at the finish there, and you realize this is, somebody's took some care with this car. This I call old school. In other words, you've got an air cleaner under the hood, and you've got a Holley carburetor on there. Now I want to pump 869 CFM, so I better buy me a 850 Holley. Okay, I got my 850. And I've got my air cleaner restriction. I've got my 850 Holley. About a pound of loss there. In other words, 850 Holley is rated at 1.5 inches of mercury pressure drop, or 3/4 of a pound pressure drop through that carburetor. I'm losing density. And the air filter is probably worth 1/4 of a pound of pressure drop, even a really nice one.
So it's reasonable to expect that we would lose about a pound.
Right, we're going to lose about a pound.
Across that combination.
Also, we've got coolant, and I don't know what you're running for your coolant temperature, but nominally a couple hundred degrees, or 190 to 210, somewhere in there. On an average day, the underhood temperature would be at least 140.
We've seen that a lot in the kind of testing that we do.
And that kind of gives us a little bit of a problem there, because we're losing density due to that.
Right.
So the pressure decrease of 1 pound from 14.7, we're now at 13.7 pounds of pressure, and we're at 140 degrees. The pressure decrease is 6.8%. The intake density decrease is 19.2%.
Significant.
So, So now our intake density is down to 61.7 pounds per cubic foot from 76 and change. It's the same engine, it's running the same RPM, but what's going to happen to the horsepower? the power output, instead of 664, the installed power in that car is going to be 537. The only thing you can do to prevent that is get current, get modern. But that is an old school hot rod.
Yeah.
And if I wanted to build an old school car, I'd build it exactly like that. And the hell with the horsepower that I lost.
Yeah, make it up somewhere else maybe.
Well, unless I'm racing it, if I'm racing a lot of cubic inches or something like that, then we've got a situation here.
Right.
If I'm racing this, I don't want to do this. So my answer to this is 537 horsepower, not in my shop. I want to make some serious horsepower. I want to make my eyeballs bounce off the back of my skull.
And you're not
when I drop the hammer, boom, eyeballs in. Pop the chute, eyeballs out. That's what I'm looking for here. So I need to boost the ID, the intake air density. That's what I need to do.
It's the only way we're going to get there.
Yeah, it's the only way we're going to get there. Notice I didn't say air pressure. I didn't say boost the air pressure. Because air pressure, as you just saw in that example, air pressure only indicated a 6-point-something% loss, but the true loss, when you consider temperature as well, was 19.2%. You're starting to get the idea that the boost gauge isn't really telling you true.
So now we're gonna. So we obviously need to increase the intake air density. We've talked about different ways that we can achieve that. Just looking at the intake system, we can do some things with ram air, and we can optimize the air getting into the engine. But tonight's topic is
before you go to the topic, I already did it, but I didn't put it in here. I took that Chevelle and put a ram air system on it off the nose of the car under the bumper. Put injection on it where I didn't have Venturis dropping the pressure. And my power loss was not 19.2%, it was 1.9%.
So you preserved a lot of that available
almost all
density.
of it.
Yeah.
You know, the thing is 640 something instead of 537.
Yeah.
Same engine, sitting in the same hole, breathing in the same air. Well, not the same air, because it's cool air now.
Because it's cooler, sure.
Yeah, it's just not in here. I didn't want to break any hearts. So, go ahead.
So we get to talk about density machines. That's kind of how we introduce the topic tonight. And we've got some examples of different types of density machines
We've got some density machines right here. There's two types, positive displacement and centrifugal. Positive displacement superchargers literally beat the air into the engine.
Yeah.
They grab it, put it in a cavity, run it around in the housing, and push it into the engine.
Into the manifold.
Yeah. You know the air's going in there. It has no choice. And the only way you can slow down the pounds of air is with the throttle.
Got it.
So this engine has no intercooler, and this is what we're talking about tonight. We're talking about engines without intercooling.
Right. We're just talking about the density machines that are going to pressurize the air.
Yeah.
And just to make a quick point here, just to make sure that we're kind of all on the same page, in this positive displacement supercharger application, we're driven by the crankshaft.
Right.
Which means
it's pulling power off the crankshaft.
The crankshaft is we actually are going to take away some power from the crankshaft.
That we are.
To drive that positive displacement supercharger. Yes. In the case of the turbocharger, we're driving
it off of exhaust energy.
Driving with exhaust energy,
yeah.
Which also will contribute some power. Is going to take up some power because we still got to push those exhaust gases past the turbine.
Right.
So we're going to have a little bit of loss there. But we may be able to get some better efficiency.
The cool thing about a non-belt-driven centrifugal, which is a turbocharger, to me, a belt-driven centrifugal is a belt-driven turbocharger. The cool thing about this is when you pull the power off the crank nose, there's a whole bunch of stuff that's worrisome. First thing is you got this belt load deflecting the nose of the crank, and they're just not designed for that.
Yeah.
But you can you could overcome that issue. Main thing is, you got to make more cylinder pressure. You got to pull in more air, make more cylinder pressure to make the horsepower to overcome that rascal.
Every bit of power that this requires still has to be
has to come from the crank. You have to make it in the engine, and it's like you have a dyno on both ends of the crank.
Yeah.
This one isn't reading anything, but it sure as hell is consuming power. And I've got a righteous example of that in a few minutes. So
different types of compressors that are going to do the job of compressing the air, increasing air density.
Right.
But we've got some efficiencies to think about. And there's going to be different types of efficiencies that we're going to get
for
at.
Different
Obviously,
types
we've got
of blowers.
different styles here.
Now, when we talk about efficiency, before we talk about efficiency, I would like to address the advantage of driving the supercharger with a turbine over driving it with a belt or a chain or gears or whatever you're using. When you drive it with a turbine, yeah, you're putting back pressure on the pistons, and that takes a little power out of the engine. It's a pumping loss.
Yeah.
But you're also using exhaust energy, which you don't do with a belt-driven.
Yeah.
So you're getting two types of energy, a little bit of exhaust pressure and a whole lot of heat. So when the exhaust goes through the turbine, the pressure drops from the inlet to the outlet, and the temperature drops from the inlet to the outlet, because we're using pressure and temp. They are just easy on the engine, and you'll make more power at any air density.
So we get the added bonus of using that temperature as a driving element.
You bet. Let's talk compressor efficiency. You led us into that. The Roots, if you look at a Roots blower, they're the lowest efficiency of the group. In their standard form, about 45%. What does that mean? That means they make a lot of heat while they're pressurizing the air. And as we know, heat is the enemy of density. So low percentages in compressor efficiency are not what you want. You're looking for high efficiency.
So the fact that it's less efficient is the result of an increase in temperature as that air is being pressurized.
Yeah, and as I mentioned earlier, you know, until people started applying science to the Roots blower, and the one on the supercharged Corvettes or the supercharged Shelbys or the supercharged Cadillacs, that 2300 Eaton, that's a 4-lobe Roots with a 160-degree twist in the impellers, and it takes out that peak shocking of the air and gets it a lot more efficient, closer to the screw. Okay. So the screw, originally called the Leichholm, is a product of Europe, and how they machined them before we had 5-axis CNC machines, I cannot figure out. All I can tell you is somebody in Switzerland made those things, or Sweden or wherever they were. Yeah. And they did it this way. It's amazing. Today, they're much easier to machine. So they'll hit around 65% on average. Centrifugals or belt-driven or turbos, 75%, and actually some of the racing stuff is well into the 80s. So it's not adding a lot of heat. When you get a pressure number off one of those, it's mostly pressure increase rather than heat causing.
So yeah, 100% efficiency would be we're increasing the pressure, but we don't increase the temperature at all.
Temperature.
Which is essentially impossible. When we pressurize air, we are going to heat it up. It's just a matter of how efficiently we can do that.
Yeah. Maybe if you did it slow enough, okay, you would not increase the randomness and the chaos. Yeah. In the air.
Of course, nothing about what we're doing here is slow.
Exactly. So these are, we talked about drive power requirements as well, and turbos are best in that respect. I want to talk to you guys about a project I did some years ago. It was the Hot Rod Magazine blower test, and it was a there were a range of blowers to be tested. This was in the late 70s, let's say 78, best my memory. And they asked me to supervise it because I was so into turbos, I wouldn't even say supercharger. I wouldn't even think supercharger. So they said, okay, you know about forced induction. How about you supervise the testing? And they didn't want me to use my dyno or my facility. They just want. So we went out in the valley. A guy had a real nice engine dyno, well instrumented, nice setup. And everybody who had a supercharger for a 350 Chevy, a small block Chevy, we got an engine from Comp Cams. They donated the engine. And we started the program. And so the engine was common, the fuel was common. What changed was the superchargers.
Okay.
We got we're breaking in the engine and it failed the rockers. It kicked some rockers out. And so we called Comp Cams and this is way back. Mark Heffington owned Comp Cams at the time. And they didn't have any instant replacements, so that they thought would not break at the time. And so Hot Rod bought one of my marine engines, one of my 350 Chevy basic engines, which made around, with a 4-barrel on them, they made around 302, 303 horsepower. We took that over to the guy's dyno shop, broke it in, and started testing blowers. And I'm proud to say it tested every one of them and it was smiling at the end. But we got to one of the blowers, and it was a blower made by a company called Mach 2. That was the name of the blower, Mach 2. Anybody old enough to have ever heard of a Mach 2 supercharger? I love it. I love it. All right. Steve Pick machined those superchargers. It was his gig. Steve was machining Keith's aluminum blocks, and he got on this gig where he was hanging around with a guy, Gary Kegel. Kegel got these World War II or Korean War cabin pressurizers, which were centrifugal blowers, and tried to run them on a fuel car. Remember that? And the only problem with the damn things was that cabin pressurizers, they don't have to be real efficient. So the impeller, the whole assembly, if it made heat, that's fine because it's 30 below outside the airplane, and you're pulling in and pressurizing air. If it heats it in the pressurizer, well, who cares?
Never even know.
Yeah, that's even better.
Right.
You know,
it's a benefit.
Yeah. So the Mach 2 blower had an impeller in it like a cabin pressurizer. It was just straight vanes that went out. It was a centrifugal, but the vanes were straight. That was last done on a racing engine by somebody knowledgeable, by Harry Miller in 1928 on the Miller 91 Indy engine. But that's in 1928, and we're not talking 1928 here, we're talking 1978. So 50 years later, it's like, what the? We put the thing on the engine. And this was the worst supercharger ever tested because it made 10 pounds of boost and no additional horsepower. Now you might say, how is that possible? How could it be that possible? The fuel flow went up, and you know, I'm looking at the flow meter, and back in the day, we didn't have the sophisticated digital jive. We had the guy that went up and down in the cylinder, and we're reading the flow meter, and I'm going, man, this thing is, you know, it was about 500 brake spec, about a half a pound per horsepower hour, naturally aspirated with the blower on, and the fuel flows up to like almost 3/4 of a pound per horsepower hour. Like so a 50% increase in fuel flow.
It's doing something. There's fuel's going away.
And the plugs are righteous. You know, I'm jetting and screwing around. When I'm done, we make the pull, read the plugs, everything's happy. We did not have an O2 sensor.
It's a little early for that.
We did read the mixture on the plugs. So I'm going, whoa. The financiers were a bunch of Apple guys from up in Washington State, the money guys on this deal. They were there, and they're going, oh my God, what could be wrong? And graciously, the Hot Rod Magazine guys let them withdraw from the test. So we finished the test, and then they hired me, the Apple guys, and you guys that have been to Bonneville probably know a few of these Apple guys. They run streamliners and stuff, the Washington State and Oregon guys. Anyhow, they said, we'll buy another engine from you, will you dyno it? So they came down to San Gabriel, where we were at the time. We ran the engine, 303, 304 horsepower, put the blower on. I already knew the jetting. Made a pull, 303, 304 horsepower. It's like if I had tried to do this, I could never do it in my entire life. You know, it's like, how do you do things like this? So the power gain that we got with this supercharger equaled the parasitic horsepower required to run it. It's like, you gotta be kidding me. So
in that situation, having boost did absolutely nothing for improving horsepower.
actually it did improve horsepower. It was heating the air a lot, to be sure, but we were running on 100, 130 avgas, so we didn't have a detonation problem. But the point here was, yes, it made more power, just enough more power to run itself.
Yeah.
So I had a dyno on each end of the engine. I just don't know what the front one was absorbing, but I could pretty well calculate it from the additional fuel flow.
Yeah.
So what I've just illustrated to you guys, and it was running 10 pounds of boost, by the way, what I just illustrated to you guys is you can have 10 pounds of boost and not gain anything. There's a prime example of it. Now I'm searching for that Hot Rod magazine or pictures of this thing for this deal, and I have failed to find them. But I found the table of contents online. They have some site has a table of contents for every Hot Rod magazine, so I know what issue it is. I got to find it. So let's ask a question. If we double the boost pressure, do we double the intake density? Any opinions on that? You create too much heat, it's impossible to double the density because the compressor, no matter what it is, to your point, creates heat. And we just saw in that first example what heat can do to you.
Yeah.
In a minute, we're going to show you in a kind of a live example. So I want to do some comparisons at equal boost pressure. And we're going to assume that we have adequate octane to do these comparisons. We're going to talk about a roots blower. And there's the roots blower setup in the Studebaker. But inside the roots blower, the impellers, I talked earlier about how the impellers look. The early ones, and I'm sorry for the ones that they're black because they're coated. But the straight vein is the traditional roots, and in this 671, there's 3 lobes. This is a straight vein Eaton with 4 lobes. The one next to it with a twist in it is that what they call TVS Eaton, the current technology they're running on the Corvettes and the Caddies.
Yeah.
So let's look at a Roots supercharger. What you've got here is, on the left, we're reading pounds per 1,000 cubic feet. On the right, we're reading boost. Now, when we look at the Roots example, Roots supercharger, we're going to run 14.7 pounds of boost. And is the first one pressure?
Yes.
So that will be a total pressure of 29.4. 29 point.
So Doubled from
4.
atmosphere.
There we are. And we've taken ambient pressure and we've added 15 pounds to it. So a boost gauge would read 15 pounds.
Right.
Okay. The density has gone from 76 to, it's doubled.
Right.
But we haven't put the temperature in. And this roots the temperature out of the blower due to its low efficiency at this boost level is 305 degrees, which is this one. Now, you notice the boost is still there, guys. Whoa, what happened to the density? It was 150 some pounds per thousand, and now it's 104. So essentially, what's occurred here, it's actually 103.8 pounds per thousand cubic feet right now. That's a 35.9% increase in density. And your boost is still reading 100%. So the boost gauge is showing you've increased the pressure by 100%. And the density gauge is showing you didn't increase the density by 100%. You only increased it by 35.9%.
So once again, the boost gauge is not an ideal reference tool for us to learn how it's going to impact our air density. It's not the best tool.
Well, for years I've talked boost.
Yeah.
It's only maybe 7 or 8 years ago that I realized, this is not a good indicator as what the hell's going on with a supercharger or turbocharger. Air density is the best indicator. So let's go back to our next example here. So we just looked at the roots. There's your 35.9%. There's your 103.8 pounds per thousand cubic feet. So if I've got 35.9% more air density, what do you think my power increase is going to be? 35.9%. And if I apply that to our original engine, we're now up to 902 horsepower. Sounds respectable, but you've got to subtract the blower parasitic from the 902.
Right. And at this point, we don't really know what that is. But
we don't know what it is, but we know it's a significant number.
Yeah.
So let's move on. Let's talk about the screw supercharger. This is a Lysholm style screw supercharger made by Art Whipple. This is my little 427 diesel that's in the top dragster over there. So here we've got a screw type blower. What does that look like inside? There you get an idea, quite a bit of helix angle, but screw type blowers are kind of unique. The impellers don't match each other. Let's show the impellers. There you see, you got if you will, a 5-lobe and a 3-lobe. So not only do they not match each other, they do not run the same speed. So if you drive on one, the blower turns faster with the same drive ratio than if you drive on the other. And in the bigger versions of these Whipple blowers, you can do either one. So I'll show you one of the bigger ones in a while. So let's look at the numbers on this one. Okay, we've got the screw type. We've got a lot more efficiency. We're still running the same manifold pressure, 15 pounds, 14.7 pounds of boost, but our air temperature is 233. So if we pull this baby down to 233, here we've got a new density. First of all, we've got 115 pounds per 1,000 cubic feet. Our density is now 50.1% greater than it was. Boost is the same. So all we did was put a more efficient supercharger on the same engine.
Yeah.
Now, if we go back, we can have a look at the results of this. There we go. So our boost is still 14.7 pounds. Temperature is down to 233 at that boost. The boost increase is still 100%, but the ID increase is 50.1%. That means we can make 50% more power. So now we're up to 996 horsepower minus the blower loss. And these blowers are a little more efficient. So the blower loss isn't going to be as great. Now we move to the next step, which would be the turbocharger or the centrifugal. And here you've got an underhood where the air is feeding into the turbochargers. There's one turbocharger on each side of the engine, and the air is feeding in through those large rubber 90s. And the duct from the nose of the car rams the air up into the compressor on the turbochargers. So basically, we've got a turbine on a common shaft with a compressor driving the compressor, and the speeds of some of these things is mind-bending. Some of the really high-performance stuff we've been doing, we're well over 150,000 RPM. Now, of course, the bigger they get, the slower you can turn them, because you'll frag the impellers. But to keep the impellers together, guys are machining them out of titanium.
Wow.
So they can run real high temp and real high speed without fragging. So let's look now at the centrifugal. With the centrifugal, we're now down to 211 degrees, and or turbo, whatever we're running. So now we have 118 pounds per 1,000 cubic feet of air. We're still moving 896 cubic feet of air through the engine at this 7,000 RPM, but we're up almost 55%. So this will summarize where we're at. Boost is still 14.7 or 15 pounds. The temp is now down to 211. Boost increase is still 100%. The intake density increase is nominally 55%. We're at 118.3 pounds per 1,000 feet, which gives us something that's kind of unique here. The ID that we just read, that 118, remember that carburetor under the hood deal? Same engine? That was 61 pounds per 1,000 feet. We're now at 118, almost double.
Just about double.
And the horsepower should bear that out. And there you are, 1,028. Not quite double the 537, but we're not quite double the density. So
now, once again, we have to take away the loss from the turbo.
Right, which is going to be a lot lower. This engine will probably make like 960, 970, somewhere in there, installed. And we're only at 15 pounds of boost, and we have no intercooling. This is the little T-Bird I was telling you guys about with one of these engines in it. And we kind of modified the intake to make it real foxy. The cold air under the hood, you know, this is a cold ram air like on the Firebird we showed you, rams into the compressors, and then the boost tubes from the compressors to the throttle body go into the bodywork of the T-Bird, up into the firewall. They're all hidden, and that thing that comes out over the throttle body has the boost air in it.
Wow.
And that's an 1150 horse. Have you guys, anybody seen this car before? Pictures. Last year, that car won the Riddler. You guys have heard of the Riddler? Yeah. It's like, in my whole life, I never, ever, ever thought I'd have anything to do with a Riddler. And sure as hell it happened. It's just one of those cool old man gets a prize deals. So, you know, if you stay around long enough, even in the randomness of the world where everything goes to hell all the time, you once in a while get that cherry. And this was it. And the kid that designed it is going to Art Center. He's a fine young man. Came out of Texas. He bought that engine from me like 4 years ago. I didn't know where it was going. Yeah. Boy, what a pleasant surprise. So, super turbo. Let me show you a super turbo. this is one of my 427s. This is a diesel. You'll notice there's a supercharger up on top, and if you turn it around and look at it from the other side, there's 2 turbos on the back. So the supercharger blows the turbos. Pikes Peak. We're working on Pikes Peak right now. We're going to be running the end of the month. This is the vehicle, and maybe we showed you a little video. You guys were here last time, but it's a Detroit Diesel 60 series in a Freightliner Cascadia. The only difference between this and an actual semi-tractor, the only difference is everything. Aluminum chassis, mid-engine, engine's damn near dragging on the ground.
I think the grill is production.
Yeah, the grill's production. But there's a whole bunch of carbon fiber there. Even so, the damn thing weighs 10,000 pounds. Yeah. This is the record holder on Pikes Peak. What we're doing is a super turbo to yank this thing off the corners. Here's the front of the engine. You see the blower drive on the front is intended to run a jack shaft. Basically, this engine peaks at 2,800 RPM. Well, I want to turn the blower 11, 12, 13,000. So I can't do that all at once because I'd have one real big pulley and one little tiny one, and it just doesn't package. So we did this jack shaft to the blower, which is the next photograph. And to give you an idea of the size of the blower, there's Bob Barobe standing there, and that's the end of the jack shaft in the second set of pulleys. So we can run the blower 3 to 4 times engine speed. And there's a look into the blower inlet. We've got tape over those impellers, but you know what they look like. We already showed them to you. And out of that hole on the blower's upside down on the engine. So we had to move the sight glass for the oil level. We had to put a second one on the top of the blower because it's upside down. We'll blow out of that through a 6-inch tube into the compressor on the turbocharger. And oh, by the way, there's a Detroit diesel with a set of headers. Is that sexy or what? We're looking for 2,400 horsepower, and it's 14 liters. So this is a very serious diesel.
So the intercooling, that's going to take care of that, the other half of the density equation. The blowers, the superchargers, turbochargers, all of that is increasing pressure.
Yes.
But the intercooling is going to address the other half of the equation.
Yeah. And of course, water injection or water methanol as well. Mm-hmm. I mean, this guy behind me, we're 1,150 horsepower and there's no intercooling. Yeah. But we are using water injection or water methanol if you really want to get crazy with it. Just to whet your appetite a little bit, we took a twin turbo new BMW, inline 6, 300 horsepower, 3 liter inline 6. What is it, a 5 series?
We weren't going to do any Euro stuff here.
Every once in a while I have a lapse. You know, I do like to wave the flag, but every once in a while we do something like this. So we took that thing, we put it on the chassis dyno, 230 horsepower at the wheels. And then we started with our straight shot is the name of our water methanol. You know, it's 100 proof and everybody's smiling. It's 50-50 water methanol. So we started adding water meth and recalibrating the ECU. What the water meth does is it increases air density and it increases the octane. So it's like you're running racing gas. When we were done, we'd gone from 230 to 333 with the pump gas in the tank and no changes to the engine physically, only calibration. Yeah. 44% more horsepower, no other changes.
So there's a lot of potential there.
Huge potential. So next time, I hope you guys can make it. It'll be called Just Chillin', and we'll be iced down and 100 proof.
All right, fantastic.
Thank you all.
Thank you guys for hanging with us.